what we call the absolute refractory period. That is why the absolute refractory period happens. Now let's move on. Let's move on to the relative refractory period. Okay, so just to remind you, absolute refractory period is happening because we have the inactivation gates closed on the sodium channels. Okay, at the same time that those sodium channels are inactivating, we have our potassium channels opening, right? So if you can see that in this cartoon up here, you can also see that in this diagram down here. So sodium channels closing, that permeability is going down, potassium permeability is going up, okay? And hopefully, as you recall from when we talked about the phases of the action potential, once those potassium channels open, we get potassium flowing out of the cell, and that helps to bring the membrane potential down, okay? Hopefully you also remember that we get this kind of overshoot happening where the membrane potential actually dips below the resting membrane potential for the cell because we have these potassium channels open. So they're basically like it's an increased potassium permeability compared to at rest, right? So if you look here, we had a bunch of potassium leak channels open. If you look over here, we have those same leak channels open, but we've also opened a bunch of voltage gated potassium channels. So we have an even higher potassium permeability than usual. That's going to allow even more potassium to leave the cell because potassium wants to move towards its equilibrium potential of -90 millivolts. And that's what causes the after hyperpolarization phase of the action potential. Okay, now I'd like us to focus on this purple area right here. I want to draw your attention to the fact that sodium channels are resetting. So the inactivation gates are now open, but the activation gates have closed, okay? And also our potassium channels are still open, our voltage gated potassium channels, okay? So let's think about what would happen here if you tried to depolarize the membrane and tried to trigger another action potential. Take a moment to think about that. Write down your answer. All right, so hopefully you figured out that it should be possible to trigger another action potential because these sodium channels have reset, right? So they're no longer inactivated and their activation gates are closed. So they're waiting for a voltage depolarization in order to open again. So theoretically, if you could depolarize the membrane enough, you could open these sodium channels that would allow sodium to enter the cell and it would trigger an action potential. However, it is much more difficult to get an action potential during this period than it would be if the neuron were at rest, okay? And the reason is because we have these potassium channels open, right? So that kind of poses a couple problems. One is that you're starting at a lower membrane potential. So in order to depolarize your membrane to threshold, you're going to need a larger depolarization to get that action potential. Okay, does that make sense? Hopefully that makes sense. The second reason is if you try to depolarize the membrane, remember that these potassium channels are open, which means that potassium is just going to be able to respond to that and it's just going to counteract it, right? So you depolarize the membrane, membrane potential becomes positive. However, since you have this increased potassium permeability here, potassium is going to have a lot of opportunity to move towards its equilibrium potential, which is -90 millivolts. In order to do so, it's going to move out of the cell. As a result, it's going to bring the membrane potential back down after you've tried to depolarize it. Therefore, during this period, even though you can trigger an action potential, it's a lot harder because of this increased permeability to potassium. You have these voltage-gated potassium channels open. Potassium is just going to move to counteract any depolarization that you might impose on the membrane. Okay. Okay, so just to recap, we have our refractory period that can be divided into the absolute refractory period and the relative refractory period. The absolute refractory period happens because our inactivation gates on our sodium channels are closed. The relative refractory period happens because we have open potassium channels and an increased potassium permeability, which kind of brings the membrane potential down. Okay. One more thing that I want to mention here, and we'll go into greater detail about later, is that the refractory period is responsible for the unidirectional conduction of the action potential. Okay, so remember that an action potential travels in one direction. It starts near the cell body. It goes down the axon towards the end of the axon. It doesn't go the other way. It doesn't backtrack. The refractory periods actually have a large role to play in governing that behavior. So we'll see that in the upcoming videos. Okay. That basically wraps up our discussion of refractory periods. Here are your learning goals. Here is your vocabulary. Thank you for watching. See you next time.